Hello again, AP statisticians, back at you here with our second lesson from the first unit. First lesson was about sampling. This lesson is about experimental design. We'll get right into it here. So the first thought is understanding whether something is an observational study or has an experimental design to it. And there's a couple things that roll with each one. The first, of course, with an observational study is you're just observing something. It's observing cars in the parking lot at our high school, or it's observing animals in the wild, or how people interact with each other in a mall setting, or whatever it happens to be. Versus an experiment, there's a couple things. First of all, an experiment has randomization, which we'll get into later. Um, but it also involves imposing change. And imposing change means that you're going to apply some treatment to part of the whole group. So it might be changing the temperature for something. If you think about a science experiment, there's changing temperatures or adding chemicals or something like that, where you are looking at a before and after, a cause-effect relationship. And it's an intentional imposing of that change rather than just what happened before and after school in the parking lot. So we aren't. The parking lot could be an experiment if we actually change something about the parking or the lanes to get out of the parking lot or something like that. Um, but otherwise, we're just observing how cars move at different times of the day or whatever, versus an experiment where we are actually going to apply some treatment, some change, and the randomization piece we'll talk about more as we move forward. So the elements of an experiment. First of all, there's experimental units. Okay, and experimental units are on what are we doing the experiment? Okay, are we doing this on people? In which case we call them subjects if they're humans. So subjects is just a human experimental unit. But experimental units could be mice, it could be um, cars, it could be computers, it could be cell phones, it could be TVs, it could be, obviously any number of animals. But experimental units is what are we applying that treatment to? Okay, so who's receiving that? The factors are the explanatory variables. So the factors would be the kind of general things that we're doing. Are we changing temperature? Are we changing number of lanes in a parking lot? Are we um, adding some uh, chemical or taking something away? And so in this example below, this is has to do with how many commercials a certain company, if you think about Doritos, for instance, how many commercials are they going to get during the Super Bowl? And the two factors would be, in this case, how many commercials. Okay, so number of commercials would be one factor. So that's one thing we're going to influence. And the length of the commercials is the other thing we're going to influence. So this actually has two factors. Okay. Um, and then there's levels of factors, and the levels of factors are just the specifics of those. So for instance, for the number of commercials, it has three levels because we're going to have either one, three, or five commercials during the Super Bowl. For the length, there are two levels, which are 30-second or 60-second commercials. Okay, so in this situation, what we have here is a level is number, a factor is number, and it has three levels. Another factor is length, and it has two levels. Now, do we have to have two factors? Absolutely not. If we just said we're doing 30-second commercials, we just want to know if we're going to do one, three, or five, that would be one factor, and we wouldn't have the second factor of length. We'd just have the one, three, or five as the levels for the number of commercials. So um, it could have one factor, it could have two factors, it could have five factors. In this case, we could talk about winning the game and winning a commercial break and all those other things that could be the case. But right now, we're talking about two factors, the number of commercials and the length. When you combine all these, you get six potential treatments. So the six potential treatments here are outlined in this diagram where you have one, three, or five commercials, and they're either 30-second or 60-second commercials. Okay, so those treatments, what we would do with that then is because we have six treatments, That means if we were to set up an experiment, we would need to have 6 groups in our experiment. And what we mean by that is if you work for the marketing team for Lay's, who makes Doritos, if you work for their marketing team, you might have 120 volunteers, okay, who say, we'll be a part of this experiment that you're running, and we don't really tell them what it's about because we don't want them to be influenced by it, but we get 120 volunteers. Now notice that volunteers are okay in this case. You do not need to randomly sample here because of what we do next. And what we do next is we take these 120 volunteers and we randomly assign them. That's what RA stands for here. We randomly assign them to 6 groups of 20. How do we do that? Well, just like we talked about picking a sample. We put the 120 names in a hat, an equal size slips of paper, we mix them up, and we say the first 20 names we pick out are going to be in group 1, and they are going to get a program that has one 30-second commercial. Okay, the group 2 is going to get the 3 30-second commercials. And what we do then is we send these groups into 6 different rooms, and we give them an hour-long program. And what happens is group 1, during that hour-long program, they see one 30-second Doritos commercial. Group 2, during that hour-long program, everything else is the same except they see 3 30-second commercials. All the way down to group 6, which is the last 20 people whose names are left in the hat at the end, if you will, they are going to see the 5 60-second commercials. And what Doritos is interested in then, or what Lay's is interested in, is what were people's purchasing habits for the month or 2 or 3 prior to the Super Bowl or prior to this program and this experiment? And then what are their purchasing habits in the month 2 or 3 after this program? And they want to see basically what's the right spend, okay? Because obviously the more commercial time they get, the more expensive. What's the right spend for us to make during the Super Bowl as a company? And so if one 30-second commercial caused people to go out and buy Doritos at the same rate as 5 60-second commercials, we'll go with the cheaper version. If there was a big difference between 1 and 3 commercials, then maybe we spend for the 3 commercials. But what we have here is an experiment where we have some volunteers, or somehow we get this 120 people. We randomly assign them, and we'll talk a little bit more about that here shortly, into the 6 groups because we had 6 treatments. And we get our 6 treatments in, and then at the end we do what's called compare results. Very, very simple in that sense, where we are going to compare. And in this case, we're going to see basically what the change in buying habits was. Now, these diagrams are helpful, but within these diagrams, the AP exam readers and myself are going to still want to know, how are you going to randomly assign and what are you going to compare at the end? Okay, so these areas become especially important, where you again would have to write a sentence about those, or 2, about how you're going to do those individual things. Big picture here, as you saw there, we split experimental units into groups, okay, whether it's people or computers or phones. We impose the treatments on those groups. Okay, again, the number of groups equals number of treatments. Okay, number of groups equals number of treatments. And then we compare the results. Sorry, I ran out of space there. And we compare the results. And again, you need to explain how you randomize and how you compare. That's setting up an experiment. So the design itself, we talked about it with the Doritos. If let's say I had 30 mice, okay, and I'm testing out a new medicine, the way I would set this up then is I would say I'm going to randomly assign these mice into 2 groups of 15. They don't have to be the same size, but typically you make them the same size if you can. This group of mice got some placebo for medicine. So a placebo is like a sugar pill. It doesn't have any effect on the animal, except for it would be a mental item if it was a human. The human wouldn't know they're getting a placebo. But what the mice would do here, this would act as a control group. And what we would have then is we would understand how are the mice aging regardless, and then how are they aging if they take our new arthritis medicine or something like that. And then at the end, we compare the results. Okay. Now, we can use a diagram for this, or we can explain it all in a paragraph. If we do use a diagram, then below it, we would talk about how we randomly assigned, and we would talk about what we're going to compare at the end. And again, what we would get here is in the random assignment, you talk about how the mice all got a number or something like that. And you label them a certain way to have each number. So that'd be 1 through 30. You put those numbers into a hat, you mix them up, and the first 15 I pick out go in group 1, and then the other 15 go in group 2. And again, it's all about providing the right amount of detail here. Group 1, you'd say, would receive a placebo. Group 2 would receive the new medicine. And then at the end, you'd say to compare results, we're going to see how the mice who had the placebo aged naturally versus the mice who had the arthritis medicine and how they aged in terms of their joints from taking the arthritis medicine. One other question you might get is what's the value in having a control group here? This has been asked many times on an AP exam. Value in having a control group is naturally as a basis for comparison and to see the natural evolution over time of something, in this case, the mice's health. So again, it's about providing enough detail in your answers to make sure that you've included everything. This is where 4 sentences is way better than 2. Because it just that in that situation you're providing more detail, you aren't cutting off some things, and it's about including everything that you really know. Okay, it's nothing that's terribly complicated, but it's about having enough detail, and that's what can come back to haunt students typically. The logic of the experiment, we use the principles of experimental design. So just really quickly, this is control. Doesn't mean there's always a placebo. It just means there's always comparison. Okay, there's more than one group. There's randomization that takes place early on in the process, okay, into groups. And replication just means we aren't going to run this with one mouse getting the placebo and one mouse getting the experimental drug. Okay. We need to run this with many individuals, whether it's phones or mice or people in each group, or we need to run the experiment many times just to determine that the results we're getting weren't just a one-time result and that they are consistent over many experiments or over many mice or whatever it happens to be. When we get to statistical inference, which is the process of running tests on these, which we'll do in future units, what we're looking for is statistical significance. Statistical significance is the idea that if one group had 60% of mice improve in health and another group had 55 improve in health, what does that difference of 5% mean? Is that big? Is it small? Is it are they roughly equal? Is one way bigger than the other one? So what is that difference? So that's what we're looking for there. Just some quick common examples here of these experiments in action. Medicine, we talked about that with placebo or new medicine. Marketing, we talked about that with the commercials. Tasting food or drink, Coke versus Pepsi, Crest versus Scope or whatever it happens to be, Sensodyne. And then just other scientific applications, temperature, chemicals, and the like. The idea of hidden bias, this is most notable in the situation of medicine. If you think about the idea of if I've devoted the last 10 years of my life to developing a new migraine medicine, and now it's time to test it. If I want to test it, and obviously if I want it to do well, then one thing I could be doing is telling the subjects, the humans who are in the experiment, I could be telling them you're taking this medicine that should make you better, versus the other group, the placebo group or whoever it may be, saying this is a placebo, this probably won't make you better, something like that. So hidden bias, it wouldn't be that obvious, but hidden bias is where an experimenter is trying to influence the results to favor one outcome versus the other. In the Doritos example, if somebody wants to spend less money, they may try and kind of subtly make it so that the 30-second commercial wins. So what happens is you get double blind experiments experiments. And this is where the experimenter would not know the treatments that are being applied either. So there would be like there might be pills that aren't labeled, and so that group doesn't know if the pills look exactly the same. They don't know if it's the pill that's the placebo or if it's the pill that's the new medicine. Um, so something of that nature. Like I said, the most common example would be in medicine here, and the double blind fixes that so that the experimenter can't have the hidden bias. Okay, the other thing you could do, of course, is have a third party run the experiment, but there's still some potential issues with that if that third party has any vested interest in it. So double blind is going to be your best case scenario in that situation where nobody really knows except for in the end unlocking what a one and what a two was or something like that. Forgetting which one is the placebo and which one is the new medicine. Uh, One specific type of experiment that stands out is block design. And a block design a lot of times gets confused with stratified sampling, but again, stratification is a sampling technique. This is an experimental design technique. And in this experimental design technique, what you would do is you would take your group to begin with, whether it was volunteers or people who were randomly selected out front, wouldn't matter. Um, and what you would do is you would break it up by some variable that could be meaningful in the experiment. And a common one with this is if you think about dog food. If we're testing a dog food and we have Chihuahuas and Great Danes in the same experiment, we could get drastically different results within one group, and all of a sudden we can't tell which dog food is better. When in fact, one dog food was better for the little dogs and the other dog food was better for the big dogs. So we might run a Great Dane experiment and we might run a Chihuahua experiment separately. Okay, we wouldn't be so worried about blocking or separating these up based on what vet clinic they went to, or even if they were 4 or 5 years old. We might be interested if they were 1 or 10 years old. But what we're doing is we're breaking it up by a variable that could influence the results. Okay, so what we do then is we run an experiment. In this case, that's shown in this example here, is we are running an experiment for males, and we're running a separate experiment for females. And again, this could be because it's a beer commercial, or it could be because it's for a feminine product of some sort, um, or it could be sports related, or it could be a medicine that is known to have a little different effects on the bodies of males versus females. Um, so what we're doing here is we're finding a variable. If we say we know it affects men and women differently, then let's separate the men and women and run their own experiment for each. And this random assignment, again, like I said before, is kind of the separation point technically. And what would happen then is you'd have two different conclusions. So you might say the new treatment was better for males, but the placebo was better for females. And by having them separate, you don't get that kind of muddied waters of having the male and female results in the same experiment and say, well, we aren't getting anything clear here. So again, gender would be a good one. Age groups, even ninth versus 12th grade, or else high school, elementary, and middle school. We talked about dog breeds. All these areas where there are variables that could influence our results, it's nice to just run a separate experiment. A couple that have been on the AP exam is one about testing out a shampoo that might be different for by ages. So we block by age and have the two youngest people go one-on-one in an experiment, and the two oldest people go one-on-one in an experiment. And then they say, what if age and gender matter? Well, then it's the two youngest males go one-on-one. And you flip a coin for who gets the new shampoo and the old shampoo. And the two oldest females go one-on-one, and you flip a coin, and so on. So that's blocking, where you find a variable that's going to influence your results and just run a separate experiment for each of those groups. So stratified design versus blocking, again, stratification is sampling, and it's just about getting a population into subgroups and picking for one sample. This is no idea of running an experiment yet. So you could have stratification that takes place before you ever run an experiment, but stratification is about who you're going to pick. And keep in mind for experiments, the who's going to be there could be volunteers. In an experiment, it's the randomization that makes the difference. So in an experiment, when we block, it's about breaking them up and running actually separate experiments for the group. It's not about the equal or fair representation, proportional representation of subgroups like stratification was. Okay, so blocking is its own. You're going to run the separate experiments, however many you need to run for those groups, and you're never going to bring them back together like you do in stratifying with sampling. One last final, one final type of experiment that we'll spend a lot of time on, especially when we get to statistical inference, is matched pairs design. And matched pairs design is really what it really means here is we're going to have exactly two treatments, and it's things like taste testing or pre-test, post-test, where you are, for instance, for the match pairs for the pre-test, post-test, you are your own control group. So it's your pre-test against your post-test. So we're really only interested in the improvement. And so what might happen in that situation is we might have a bunch of students take a pre-test, and then we might teach through two different methods, and then have all those students take a post-test. Um, and then we just look at the improvement. Or as you can see here, pre-test to post-test versus pre-test to intervention. So getting some 0-hour help and then taking a post-test and seeing if that intervention is useful. So this might be something that would be tested to determine if MAST is a useful tool for students, useful opportunity for students. But you are your own control group, and the randomization is just are you going to be in the intervention group or the non-intervention group here? But ultimately, we're still just interested in that relationship versus that relationship. Another one is taste testing, and this is a common one. So if we wanted to do a Coke versus Pepsi experiment, what we might do is we might take 50 volunteers. Okay, it's fine that they're volunteers. We're going to randomly assign them to two groups of 25. And what we're going to do is the first group of 25 is going to try Coke and then some sort of palate cleanser like a cracker of some sort, and then Pepsi. And the other group is going to go Pepsi, then Coke. And it's important to switch the order here because it might be that the first sip is the most thirst quenching or something like that. And so you need to have 25 going each order. But then at the end, you're going to compare the results by just taking the ratings all as one group of 50. So what you might do is, for instance, Pepsi minus Coke is all you're interested in, and you'll take all those ratings for all 50 individuals, take their Pepsi rating on a 1 out of 10, take their Coke rating on a 1 out of 10 and subtract, and you're really just trying to see if that difference is 0, then that means they found them to be equally good or bad or whatever. If that difference is really positive, then they found Pepsi to be better because that was the first one we put there. If it ends up being super negative, then it would be Coke. And what we want to do here is we're going to test to see if it's 0.5, is that something that's statistically significant? And that's what we'll follow up with later. But that is a matched pairs design. And again, the most common are these two, pre-test, post-test, and then like the two products testing. The last thing to mention here is confounding variables. I mentioned this a little bit with blocking. Confounding variables are just other variables to be factored in that could influence the results of an experiment. So for instance, if you didn't break up the dogs by breed and you were testing a dog food, a confounding variable might be how many big dogs got randomly assigned to one group and how many little dogs got randomly assigned to another group. If it's pre-test, post-test, and you were just testing the intervention, but some students went home and studied for a bunch of hours or did a lot of homework and other students didn't, that could be a confounding variable. In the Coke Pepsi example, what if one of them's ice cold and the other one's room temperature? That could be a confounding variable. So you do want to be aware of anything that can influence the results. And a lot of times we'll try to block to remedy that, like with the dog breeds. But sometimes you can't. It's just it's a mistake or an error on the experimenter's side, like if Coke and Pepsi were tested against each other and one was ice cold and one wasn't. We'll leave it at that for now. Please let me know, as always, if you have any questions. Thanks for listening.